Okay guys, I'm just here really briefly to talk to you about the extension of the invertible matrix theorem. Didn't quite get a chance to do that in class on the other day, so I just wanted to put a few more statements down in this theorem that we can now talk about since we've been covering the chapter on vector spaces. So a few more things that we can say. Now, just to remind you what the theorem was, this is the theorem that basically has a bunch of statements about a square matrix A. So A is an n by n matrix. The following things, this list that I'm making, everything in that list is true about the matrix or false about the matrix. So if I give you any matrix, either everything in this list is true or everything is false. Okay? So it's just a bunch of things that are all kind of equivalent. So of course, A being invertible is the first one. And what I've got here on the left side are all of the statements that we learned before, right? So things like AX equals B has a unique solution. The rank of the matrix is n. A is row equivalent to the identity. You can row reduce it all the way to the identity matrix. And this is the one we use a lot, right? The determinant of A is not 0. So all of these things are true about an invertible matrix. But there's a bunch more things that we can actually say as well, and I want to talk to you about that and add to our list here. So on this side, I'm going to add a few more things to the list. Okay, so we're going to go all the way from H up to P right now. Okay, so you might remember the rank. I hope you remember the rank nullity theorem. Tells you that for any matrix, the rank plus the nullity adds up to the number of columns of the matrix. So if I have a matrix of rank n, then its nullity, as you no doubt realize, would then have to be 0. So that n plus 0 adds up to n. The nullity, by definition, is just the dimension of the null space. If something is 0-dimensional, it really means that it is so small that there's nothing there, right? So the null space of the matrix would have only the 0 vector in it. That's the trivial subspace. Kind of follows from item C on the list, in fact. If you look at the solutions to AX equals 0, that tells you what your null space is. Well, here it is. If A is invertible, the only thing in the null space is the trivial vector, right? So it's a very, very small null space in that case. So that's item I. Okay? Then the next few things have to do with the columns of the matrix. Okay? So one thing that you won't be surprised by is that the columns of the matrix A are linearly independent. So if you take each column of the matrix and treat it as a vector, say a vector in Rn, right? This is an n by n matrix. So each column is like a vector in Rn. Those columns are linearly independent. Okay, makes sense. If you row reduced the matrix, you would get a pivot in every single one of those columns. There would be no free variables. There would be no unpivoted columns, right? So the columns of A are going to be linearly independent. In addition, you can also look at the span of those columns. And because we basically have n linearly independent columns in Rn, right? So we have, the matrix has n columns, and each one of those columns is in Rn. So I have n linearly independent vectors in Rn. Well, then if they are linearly independent, then they also have to span the space, right? If I give you the right number of vectors, Rn being n-dimensional, I have n columns. Then if those columns are Li, then they also span the space. It's either both or neither, right? It's either both or neither. So the columns are Li, the columns span Rn, okay? And of course, if they are Li and they span Rn, then we're really just saying that the columns of A form a basis for Rn. So columns of A form basis for Rn. Okay? So that's J, K, and L. And the next three statements are basically the exact same thing about the rows. So M, N, and O are just going to be exactly the same thing about the rows. So the rows of A are linearly independent. Okay, remember, linear independence is like a good thing. Okay? Spanning the space is like a good thing. Being invertible is like a good thing. Everything in this list is like what you would want, right? It's like good conclusions. Okay, the row space of A this is equal to Rn. All right, and then the rows of A form a basis for Rn. Okay? And then finally, because it doesn't matter whether you talk about rows or columns, if A is invertible and you switch the rows with the columns and you look at A transpose, what was true about the rows of A becomes true about the columns of A transpose, and vice versa. So A transpose would also have to be an invertible matrix. Okay? So there's no homework on this. This is just almost like a summary of some of the theory. And it's all kind of put into this one big giant theorem with all of these things on this list. So we've extended this list quite a bit from what we had before. Now we have all of these statements about the null space, row space, and column space, and the linear independence and the basis properties of those rows and columns for an invertible matrix. Okay, that's it. Just wanted to go through that really quickly. Let me know if you have any questions, and hope it makes sense. All right, thanks.